I have some prepared notes, and I'll ad-lib after this as well. I can see it's going to be a little hard for me to see sometimes with the lights. So 5 concepts maybe that I'd like you to think about and remember as a result of this. You heard Martin talk about abstraction, and I'm going to talk about it, but a little bit differently. Systems engineering, but I'm going to be a little bit higher level than he was. My involvement at Daimler Trucks was at the level of systems engineering, partially of the entire vehicle, but also how the vehicle fit into the service structure and the dealerships and other things. And I'm going to take it even a higher level than that. And I'm going to get into modeling and simulation. Everything that we're doing in the automotive industry and the truck industry is all related to safety, fuel economy, and greenhouse gas emissions. So that's kind of one concept at all to me. And then the last thing I want you to remember is you and what role you need to play in all of this. So, good morning. I'm certain you're going to find today a lot of useful information and worth the time that you're investing in this. My job is to somehow try to connect the dots. I heard Martin say that. But I'm talking about the Department of Transportation because I'm going to take us up a level from the vehicle to how it fits into the traffic situation. A good portion of this week, I'm spending my time down at Cobo Hall for the World Congress, the 21st one of the Intelligent Systems Transportation Group. I'm getting to see demos. I'm listening to all kinds of presentations from the CEOs and the chief technology officers of the automotive companies, Honda, Toyota, the suppliers, Delphi, Visteon, Siemens are all there talking about what the future holds for us in terms of what we're going to be doing with the autos and the trucks. On August 18th of this year, just a couple weeks ago, NHTSA announced that they will indeed, as we expected, require vehicles in the future to have vehicle-to-vehicle communications. So we're going to add another computer onto the truck and the car, or we're going to add new functionality into an existing computer that we have in order to make them talk. Now, my wife has a mischievous little girl in her that refuses to get older than 9 years old because once you get to double digits, she says you have to be very nice and proper and stuff. So when I told her that cars were going to be talking to each other, she said, well, does that mean when the sleek Ferrari comes up next to the Corvette at the traffic light that it's going to turn to it and say, your place or mine? But actually what I learned on Sunday from Mary Barra, the CEO of GM, is that really what's going to happen is the Cadillac CTS, which has the vehicle-to-vehicle communications in it, is going to turn to the Corvette and say that, and the Corvette's going to just be blank because it won't have the vehicle-to-vehicle communications in it yet. The whole issue that we have to address is how long is it going to take us to get this entirely into the system of everything. So, you don't know me. Let me tell you a little bit about myself. So I've spent my career developing teams of people to bring to the market high-tech products. I've done it in aerospace, I've done it in medical systems, I've done it in industrial automation, I've done it in trucking. I call myself an intrapreneur because I'm always involved in developing new products and new business units. I've done it at General Electric, I've done it at Eaton, and I've done it at Daimler. Along the way, I've been the first employee hired into a business unit to develop it. But as part of Daimler, I've been one of 275,000 people in an organization, very highly engineered. And from talking with the mentor people, I may have a skewed view of how to do automotive engineering because of the German approach to systems engineering that I've had to live through. So I've worked on breast scanners, I've worked on cardiac monitors, self-guided bombs, nuclear reactors, programmable logic controllers, sensors, semiconductor processing equipment, radar systems, engines, transmissions, brakes, telematics, and human interface devices. In the process, I've had to make sure that they were designed right from the start. I've had to help the factory get them produced and programmed correctly. I've had to make sure the dealerships could service them. And when things did fail, I had to stand in front of a customer and explain why it didn't work and sometimes get under a truck and fix it. Through all of that experience, what I've learned is that it takes the right technology at the right time, properly done. And that's what I call savvy technology And if you do it right, somewhat what we're talking here with the Mentor Graphics approach, then you're going to create powerful results for your company. So with that background, I think I'm qualified to talk about connecting the dots and using the best tools, especially those from my sponsor, Mentor Graphics. So let's talk about connecting trucks. Let's run a video.
I've had my ups and downs, my fair share of bumpy roads and heavy winds. That's what made me what I am today. Now I stand here before you. What you see is a body crafted to perfection, a pair of legs engineered to defy the laws of physics, and a mindset to master the most epic of splits.
Who can say where the road goes, where the day flows? Only time. And who can say if your love grows as your heart shows? Only time. We gotta
When I talked about connecting vehicles, I doubt you thought I meant a physical connection with legs. Those trucks were moving backwards. I hope you caught that. And they're using an advanced driver assistance system from Volvo called Dynamic Steering Product. I wouldn't be surprised if one or more of you on the embedded software side might not be working on some sort of system for maintaining the steering on a vehicle as it's going. I've seen some heads shake, okay? So that was a pretty good video of that. But since I think we're talking about connecting vehicles in some other fashion, and probably wireless, here's an application along those lines. Let's run the second video.
Southbound trucker coming up on marker 77. You copy?
Copy, southbound truck. I got you in my mirrors.
Would you like to link up?
Okay to link.
We are linked.
Four-wheeler cut us off. Are you okay back there?
Yeah, it's all good back here.
So the name Peloton came from the group of bicyclists in a race that congregate in order to save energy. And when two trucks are in a platoon like that, both trucks end up saving fuel. The next step for that vehicle following is to be able to automatically take the vehicle in front without the driver having to stay quite as vigilant and be able to take his hands off the wheel. In that particular situation, there are radar systems for safety, and the driver in the following vehicle still maintains control by actually steering that vehicle because the vehicles are very close. It's the wireless communications from the front vehicle to the rear vehicle that allows the rear vehicle to basically brake almost at the exact same moment, obviously not really, as the vehicle in front, but much faster than the driver can react by seeing brake lights come on or sensing that he's getting closer and making a stop. So the Army has been particularly interested in that approach for several decades because one of their big problems is that young kids, 19, 20 years old, in a convoy frequently get into accidents. So we're going to talk about connecting the dots, and since this is an automotive conference, I'm going to make the rash assumption that the majority of you work in the automotive industry rather than boats or trains or planes, or even trucks like I have done. But I hope, like me, you love sleek, great-looking cars like this image of the new LaFerrari. Pretty good looking, isn't it? But I'm going to ask you, is it real? We have leaders that paint a picture with words of a future reality that's better than what we experience today. When you look closely at this picture, it's actually words, and it's words that have created that picture there. Our auto companies have visions of the future that's safe, green, and connected. They have visions of cars being able to see around corners, images of cars that can see in front of the bus in front of them. They imagine cameras, radars, lidars, and ultrasonics that can see all. They believe that carbon dioxide can be drastically reduced from transportation. And all this will be done with vehicles that are connected to each other, connected to the roadside infrastructure, and informed by the all-seeing cloud above us. These images of city streets with buildings reminds me of a close look at a printed circuit board assembly. I can see buildings. I can see defined pathways for signals. I'm aware of the electromagnetic fields that surround the traces. And I can see the signal controls, the traffic lights, from large signal processing devices. And I can take that a step further to a smaller scale and look at an electron microscopic image of an integrated circuit. And again, I see signals that are under the surface, packets that move and are controlled like traffic lights. All three levels of abstraction to me have a similar look and feel. I see the signals moving along paths on the integrated circuit, similar to vehicles moving along the streets on the cities. Therefore, to me, some of the tools that we use to design at that microscopic level of the integrated circuit or at the level of the printed circuit board should be able to be used to design at the macroscopic level of our cities and our streets. Some of the tools used for designing electronic control units, the embedded software things that we've talked about, should be able to be used to help us with the design of connected vehicles. So I asked you if the picture of the LaFerrari was real. As engineers, one of the things that cuts across all the different businesses I've worked in, it's this idea of abstraction, and our ability to create a new reality from that abstraction from one level to another. We have the ability to see the forest for the trees, yet rely on the existence of the roots of the trees. So actually, when you think about it, that picture of the LaFerrari was not real. It's only a picture. It was a collection of dots that our minds coalesced into a single image that for us was at least real enough looking, but it wasn't the same as having it sitting here with us. That principle of abstraction is critical to the work we do in computational fluid dynamics and stress analysis. In there, we define a small portion, a tiny cube in space, and use it to create a network of microscopic cubes to get a macroscopic view of air turbulence. So whether we are talking about a sleek sports car like this for that abstraction of computational fluid dynamics, or maybe we're BSing, we're using the principle of abstraction in order to do things. Systems engineering is not entirely new. It's critical to how we do things in our work. In fact, I heard, I think it was Monday at the conference, one of the chief technology officers at Ford saying that one of the things that the auto companies need is better systems engineering across the disciplines, just what you heard Martin say. Starting at the top and sequentially breaking down a task to smaller and smaller pieces, which is the second and third row there, it's almost the exact opposite of what we were just talking about, now with the abstraction going from the macroscopic level to the microscopic level. Now, I can highly recommend, if you haven't ever looked at it, the NASA Systems Engineering Handbook. It is, by the way, free online. It is a PDF. I've used it to teach some courses in systems engineering. And of course, it was significantly updated after the tragic accidents that have happened to NASA. Something that's often overlooked in systems engineering is that you don't quite always get it right the first time. In fact, I had one very capable manager who once told me that it takes 3 times before the design will really be right. And that sounds terrible, but I've actually seen it happen time and time again. And then I had another boss who was an engine designer at heart. And he told me that when you do a new engine design, it's going to have to suffer through 5 field campaigns before you get it right. Also sounds terrible, but I've seen it happen over and over again, that in spite of everything we do, it still ends up having some problems. Now, if we can reduce just one of those field campaigns, we'll have saved an awful lot of money. So that's going to take some sort of an iterative design, and that's part and parcel of what NASA teaches on the systems engineering, that you have to have successive refinement at every stage of the design. And that's why we have, in many of our businesses, we have a pre-concept phase, we have an advanced development phase, we have a pre-design phase before we finally actually get to the design phase. But as you know, it takes us far too long. Somebody said yesterday at the conference, one of the, I think it was a Honda CTO, he said, we really can do it all in a year, just like they can in the Googles and the Amazons and in the consumer electronics world. But it takes us another 2 years to make sure we test it right and make sure that it is safe and reliable and doesn't fail under any conditions. So you saw the V model, and I put in there the V model for victory, because this is indeed a key to us. And is there anybody not familiar with the V model at this point in time? I would hope not. That's good. I don't see anybody willing to raise their hands. I've used it for over 30 years, not just in software development, but in various industries. It started in software, but it's really systems engineering from the highest level to the lowest levels of abstraction, and then incrementally building the product back up. A samples, B samples, C samples. I saw that on Martin's chart. But it's also different levels of test for the whole vehicle that have to be done in different tests. And this model, how many are dealing with ISO 26262 now? Only a handful. That's surprising. Because basically this model of how to do development is becoming, if you will, a law, a regulation in our business. So when you look at it, we've got various tools that can be used, and I've tried to map some of the tools of Mentor Graphics to this chart. Now, I'm really glad to see Artisan, for instance, which is going to fit in the top level there where requirement specification goes. Now, at Daimler, we used IBM's Rational Doors, and in Portland, Oregon, there's another place, Tesla is using a piece of software from a company called JAMA to do the same level of requirement specification and maintaining that throughout the entire system. We also make use of MATLAB and Simulink and AVL and other simulation tools as we're going up on the other side of the V as we're building things back up. I'm particularly pleased to have learned a couple of weeks ago that Daimler Trucks is going to put out a new truck in January of 2017. That's public information. But one of the body controllers was designed specification-wise using IBM Doors and MATLAB Simulink, as opposed to using a Microsoft Word document that nobody would read, and if you'd said and rather than or, you'd end up with a mistake in how you were doing the design. So I'm glad that we're moving in that direction, and I'm glad to see Mentor Graphics doing in that direction as well. So let's go on. So I mentioned in the previous slide with NASA that it's important to have some sort of iterative design process to refine things. And in some of the work I do, I hear an awful lot about agile development, sprints and scrums and things like that. And I absolutely believe that those have a place if I'm doing a smartphone app or if I'm doing an IT application for the floor where I'm using a PC as the display. It's great for getting feedback from the suppliers, from the customers of your system as early and as often as possible. But I disagree with some of the things because it would say everything is like Apple, it's the experience, it's all about the user, but we in the automotive have to also think about meeting regulations for greenhouse gas emissions, for fuel economy, and for safety. And so there has to be some sort of a combination of the V model and Agile. And if I put the concept of Agile Sprint along the V, I can easily see how I could take Agile and I could have some sort of an iterative design cycle at every stage along the way. I could use it to get a little bit more done each day, each week, each month. But there still needs to be that discipline from start to finish of the major milestones of A samples and B samples and B2 and B3 and B4. And I have my first buck and I have my first mule and I have my first vehicle that's going to go out to the test track and those types of things. So that's where the Agile, I think, fits in with the NASA's concept of successive refinement. Now, you may not have noticed that in the top 2 boxes on the right, I don't show a circle. And I didn't on the other slide as well. That's because it's at some point in time, you have to stop dealing with a simulation or a model. You have to get a real vehicle out there. And so there's always going to be something at that validation level, homologation for the government, proof that you're safe and reliable, that's going to have to be done at the full vehicle level, not just an abstraction on a computer. So I've been out on test tracks. I've been on the road to complete testing. And I had a chance yesterday to go out on the road on a couple of the demos that they have downtown. So as much as possible, we're trying to take the road, what we know about that, move it to the lab, and move it to math inside our modeling and simulation. That's the only way that we can do regression testing that we need to do anytime we make a change to the system, and do it quickly and effectively. So every abstraction that we've done has involved taking something in that real world and finding a way to move it into the lab. But there are some things that don't quite fit, even though they're in the lab. They're more, to me, vehicle testing. And that's that bottom slide there, where it's testing for buzz, squeak, and rattle. So everything we're doing is trying to move that road to the lab, to the math, so that we can then have a better understanding, we can predict things. And what I'm seeing today, and I was talking with one gentleman over here who's into fuel cells, and he'll understand this, we now simulate chemical processes inside our batteries or inside the fuel cells. We simulate the combustion inside the chamber of a cylinder in the engine. We can use CFD simulation for defrosting of the windshield and determine if it'll meet customer requirements. We can look at the heat dissipation of the brakes. We can look at cooling of the driver's body and stability control of the vehicle. Last week I was in Washington, D.C. working for National Academy of Sciences Committee, and we were reviewing some of the hundreds of millions of dollars that the Environmental Protection Agency and the Departments of Defense, Energy, and Transportation spend on research. Much of what they're doing is involved in trying to create models and abstractions of the real world. And I've got a few examples that I'd like to show you. And I can't explain everything on these slides. I don't want to. You can get a copy of these slides later, I know, so you can study them. So this one was interesting to me. We talk many times about the electric motors replacing the engine because they produce torque at low speed and they're really good. Well, it turns out that an electric engine, an electric motor, also has a map similar to the fuel map of an engine, and there is a sweet spot to it. And so yes, it can produce torque at nothing, but for its most efficiency, it needs to be running a little bit faster. So the government is looking at how can we expand the island of peak efficiency, and using that in order to improve the efficiency. This is a series of slides where somebody has studied what happens with the heat inside a vehicle. In this case, it's a big truck that they're looking at. If you use black paint, guess what? It's hot inside the cab. If you use blue paint, it's not a whole lot better. If you take the blue paint and you put some sort of material into it to create some sort of a reflective capability of the solar power, then you can see it gets a little bit better. There's a little bit less red, a little bit less yellow, a little bit more blue and green showing up now. And what a shock. If you make it white, it's going to stay cool inside your vehicle. But so many people out there don't want white vehicles. They want to have some color and they want it to look like their particular brand. Modeling of our atmosphere even is another area. It's kind of hard for me to believe, but if you look at the numbers there, they're looking out to the year 2100 and predicting what's going to happen for greenhouse gases that far out. And they include the impact to temperatures and sea level in those predictions. Now these are people like myself, people from universities who have been around for years who are putting this information together and studying things. And there are models and simulations that help create these things. And those three lines in the first picture there are actually different assumptions. As you change your assumptions, what's going to happen so that you can get a range of what could be the future. So one of those that's important in this is what's going to happen with fuel. Over the last 5 years, we've changed from being a net importer of fuel to being a net exporter. Natural gas and horizontal drilling and fracking have dramatically changed what the future looks like for the United States. And what you see here is combined with that and the fact that the light-duty vehicles have a strong CAFE regulation, the light-duty demand for fuel is going to stay somewhat level out through 2040, but for heavy trucks, it's going to continue to grow because we're having more people, they're going to need more freight delivered to their homes. Now, why are the CAFE regulations? California Air Resources Board has been a leader in demanding that we reduce NOx and emissions and improve fuel economy. The fuel cell vehicle, California will have next year, they're supposed to have 5 different manufacturers producing fuel cell vehicles for hydrogen there. They have the hydrogen infrastructure already being built out. And so they're very big on the electric vehicles. They're driving it. There are 9 to 10 states that are following their regulations, and that's what's going to improve the fuel economy regulations for the passenger cars. An important area is we still don't entirely know how a fire starts inside the cylinder of an engine. It's just amazing to me, but there is an awful lot of research still going on to figuring out how to get that fire to occur and burn the fuel absolutely cleanly, absolutely completely, and produce the energy that we need. Now, this slide is looking at different ways of modeling. In the first red column is the experimental results. Then in the second column is some low resolution simulation results. And then the third column, labeled LENS or LES for large eddy simulations, shows much more capability there. And I think on this one, each cycle 1 month on 256 cores. So one simulation takes a month on 256 processors. So sprays, it's no longer enough that we have pre-injection, multiple injections, and then multiple post-injections. Now we actually have in production nozzles that have multiple holes so that they're spraying the gasoline or the diesel in multiple directions. And note on this one that in the in the right column there, it says each simulation 1 month on 64 cores. Okay, that's better than 256. That's an improvement. Genetic algorithms. I must confess, I do not yet know what a multi-objective genetic algorithm is. And I can see in the bottom right that the simulation takes, only a week and on 24 cores. Well, that's better than the last one. What that tells me is that I'm willing to bet that 10 years from now, we're going to have an engine control in the vehicle in 2025, and it's going to be able to do these calculations for whatever this algorithm is in real time on the engines in production. In 1974, I worked on the first X-ray based computerized axial tomography device, CAT scanner, for breast scanning. And this year I had a chance to visit the Pacific Northwest National Lab, and I saw the same mathematics that was used in that design in 1974, but now 40 years later, it's being used with neutron radiography that has the capability to see through metal, not just soft water-type tissues. In fact, I'm astounded, flabbergasted at the number of different models, simulations, and abstractions that exist for everything from the microscopic world of electrons and droplets of fuel to the highest levels of our economy. One of my activities is looking at technologies that are going to be in 2025 in production and cost-effective and reliable, and beyond that time frame as well, for reducing carbon dioxide for trucks and improving the fuel economy. Some of the people on my committee are also working on the light-duty side. It involves alternatives for certification of the vehicle. In the passenger car side, we take a whole vehicle, put it in a whole vehicle dyno. On the truck side, we don't do that. On the truck side today, we will test an engine in an engine test cell, and it's not even on this slide. It would be off to the bottom right as an option. We do have a very simple model with MATLAB Simulink base that you put 5 parameters into. How much does it weigh? What's the rolling resistance? What's the aerodynamics? Do you have a speed limiter? And do you have an idle device? And it determines whether or not you meet the regulation or not. But in March of next year, we're going to get new regulations for 2020 timeframe. And so in 5 years, we may be testing the engine and the transmission together. That's what you tend to see here is a picture of the engine and the transmission along with the axle and the drive line. And we're going to do it all as a single entity. We're going to have software involved that controls it as well. And we're going to have better simulations of the road that has to be done rather than some things that you may have heard called SET and FTP cycles. Because it's important to know how a truck or a car is really operating. You may be familiar with some of the lawsuits that came out because, you know, this car said on the sticker, I'm going to get 35 miles per gallon, but they were only getting 24. We want to avoid that in the future and make sure that what we design to is what is really needed in the marketplace. In China, an entire vehicle, an entire truck has to be tested on a dyno, much like the passenger car. That's represented by the option in the bottom right corner here, which is one end of the spectrums of how we're looking at certification for trucks. But there are a lot of people who are actively lobbying for the other end of the spectrum in the upper left, which is full vehicle simulation. So we would do the certification entirely based on a simulation model. We would certainly have to verify the model, but as you make changes, you would only do a simulation, not have to actually test a vehicle. And that's largely because the trend toward that direction is trucks are much more variable than the passenger cars are. You may not think that, but when we only produce 2 trucks that are the same at any point in time, it is different. Okay? So that brings me back to talking about the intelligent transportation system and its architecture, and where I'm spending a lot of my time this week. It was like 10 years ago, probably more like 20 years ago, since this is the 21st World Congress of the Intelligent Transportation System, that people began to think about how to design the entire infrastructure, the traffic signals, the speed signs, the cars, and all put them together as a single entity. And they abstracted a system down, and it has different levels, and it uses all of the principles of systems engineering that we've been talking about. Now, one of those challenges for the connected vehicles is the fact that the infrastructure is not controlled by one big entity. So when you deal with Boeing to design an airplane or Airbus, they've got control over kind of everything, and they deal with the FAA. But with this area, Troy is different than Detroit, is different than Livonia, is different than Ann Arbor, is different than Ypsi. And so they have their own budgets, they have their own traffic engineers and everything else. And so it is much, much more difficult to get cooperation than even in a vehicle OEM would be in order to do that. So that's a challenge. The funding for roads and bridges and tolls is done by state or by the municipality. But in spite of that, we do have some portions of it that have been implemented. We do have buried inductive loops in the road that control the traffic lights. We have incident management centers that use traffic cameras to monitor activities. We've got road signs that give crowdsourced information on how long it takes to get someplace, and signs that'll tell us, it's 10 minutes to I-75. We have cell phone communications with way stations that'll allow a truck to keep on trucking and not have to stop. We have automatic toll collection systems that will painlessly separate us from the abstraction of money in our bank accounts. And I see much more opportunity to apply these tools of abstraction and modeling and simulation and systems engineering in the next decade as we try to get from where we're at today with single vehicles to the connected vehicles that people believe are happening. And so I see us treating this as independent parts of a control system. I can remember when we had no ECUs. I can remember when we had one ECU and everything was wired to it, and we had a closed loop control system. I have helped all of you live through, now we're going to put a smart sensor out there or another computer, and it's going to send us information over a network of some sort of communications. But now we're talking about taking that closed loop control system and making it even bigger, because whereas today a fire and emergency vehicle can tell a traffic light to turn green, the next step that I was hearing about this week is instead of waiting till you get to the light to turn it green, what about those 20 cars that are in your way and going to stop you from even getting through it? So instead, they're now going to be able to tell the light to change maybe 2 minutes in advance, clear the area, then turn it red so that nothing happens, turn it red for the right direction, and then be able to have it clear for that fire engine to get through. For a hybrid vehicle to be able to know what the traffic lights are doing and interact with them. For trucks that are platooning, to know that, I got to let that second truck get through too because I'm a long vehicle. Those are the things that we're going to be doing. So I see tremendous possibilities, and I know there's an awful lot of work to do to make sure that these connections are safe, environmentally friendly, and reliable. And I guess that's because I'm an engineer, and through time, I have learned that, and I've learned it the hard way, that we engineers think differently than most of the population of the world. There's only a few of us compared to accountants, lawyers, salespeople, marketing people, etc. So let's run a video.
I'm worried about little Dilbert. He's not like other kids.
What do you mean?
Yesterday, I left him alone for a minute, and he disassembled the TV, our clock, and the stereo.
That's perfectly normal. Kids take things apart.
Ooh. The part that worries me is he used the components to build a ham radio set.
Oh dear.
Is that bad?
Normally I'd want to run an EEG on him, but the machine isn't working. It's worse than I feared.
What is it?
I'm afraid your son has the knack.
The knack?
The knack. It's a rare condition characterized by an extreme intuition about all things mechanical and electrical, and utter social ineptitude.
Can he lead a normal life?
No. He'll be an engineer.
No!
There.
But take heart. As engineers, we are never satisfied. We keep asking, what if? We can imagine a better world, and we make it happen. So let's run this next video.
That's one small step for man, one giant leap.
Hey Allie, what are we working on today?
Hey Andrew, I've got a new design for the air quality monitor. Want me to send it your way?
Yeah, send it over. I'll take a look.
Okay, here you go.
Got it. Looks good. I'll send it over to the 3D printer. Alright, the prototype looks good.
Alright, awesome. Hey, do you think you could check up on the new solar plant?
Yeah, sure. I'll head over now. Take me to the solar plant. Hey, I'm at the solar plant. Everything's running smoothly. We're making about 1 megawatt of power.
Awesome, good work today. I'll talk to you later.
Alright, talk to you later. Bye.
So I know we're headed to a future that's absolutely more connected than ever, and it can't be done without all of you. And I'd be happy to take some questions. And remember, abstraction, systems engineering, modeling and simulation, safety, fuel economy, and greenhouse gas, and you're part of making it all happen. Thank you.